Thank you. Good afternoon, everybody.
Good evening. My name is Loewes.
I'm Guimaraes.
Today we're going to be talking about parameter reconstruction and estimation of widths in Coherent elastic neutrino-nucleus scattering experiments. With that, we're going to start with a short discussion of short baseline sterile neutrino searches, the minor experiment at A&M, Bayesian and frequency statistics, multi-nest, deja vu, a toy model where we discuss a lot more into multi-nest and applications future goals.
So let's start talking a little bit about investigating sterile neutrino hypothesis with coherent neutrino-nucleus scattering. So those are the two main ideas that we're going to be marrying together in the project. As has been already explained, coherent neutrino-nucleus scattering just means that the momentum exchange is small enough such that the Brown wavelength is larger than the scale of the nuclear atom, and the different nucleons cannot be resolved. Sterile neutrino hypothesis states that there might be a fourth neutrino that does not interact through the weak nuclear force. And there have been some experiments that have shown a deficit of the neutrino flux with respect to the expected one. And one of the possible explanations for it might be the sterile neutrino hypothesis. So the two parameters that are predicted they are expected from the model are the mass gap squared and the mixing angle. This plot on the left shows a deficit of the flux due to considering or expecting the sterile neutrino hypothesis. The y-axis is the deficit, which is scaled by the mixing angle parameter, and the x-axis is the distance that you get your detector from the source, which is scaled by the mass gap squared. On this plot, each of the lines represent each a different energy bin of 1 electron volts. And we can see that in this region, for very small lengths, there's not much deficit because there's not enough time or length for the neutrinos to oscillate away. And for very large distances, all the effects average out. So there's nothing very interesting to be observed there. The most interesting part is this region. And we can see that for a given shorter distances, the smaller energy bins or small energy neutrinos seem to show a higher deficit than the higher energy ones. And as you go further and further away, the higher energy neutrinos seem to show a bigger deficit. So there's this switch after some point. And if that can be observed by measuring the neutrino flux at different lengths, it can be a smoking gun for the sterile neutrino hypothesis. So, some questions of interest that we're going to try to explore is if I give it a data set, so what are the parameters that I can set to my model such that it will best predict the data that was outputted? For which experimental layout, meaning the parameters, exposure time, length, whatever other external parameters I might have, can we optimize the coverage of the parameter space? And how can we estimate the width of the parameters given our systematic and random uncertainties? So, some goals for our project: hopefully exclude much of the parameter space, maybe rule out the null hypothesis, explore the 1 electron volt sterile neutrino range, reconstruct the two parameters, mass gap and mixing angles, and optimize the distance and exposure balance in a neutrino experiment.
Moving forward, it's going to be important for us to discuss the underlying statistics involved with this. First things and foremost, frequency versus Bayesian approach. The easiest way to explain this is if I lost my keys, where would I look for them? I wouldn't look everywhere and anywhere for them. I'm going to look the places I'm most often to be: my bedroom, my dorm room, my desk, my car. We think of this as a prior. The prior comes in with Bayesian statistics as well as the likelihood function, the posterior, and the evidence involved. And we're going to use these different portions of it to solve for the missing piece of it. Quick reminder of likelihood functions. Simple idea, we're going to be looking at Poisson and Gaussian distributions. What might not be familiar with you guys is this S term right here. We're using this as a strain term with it. We're going to think of it as a ruler. If we're going to fit a ruler to a line, a straight line's going to fit real well. I'm not going to have to put much effort into it. I can just stick that ruler up there. But if I was going to do a quadratic or a sinusoidal curve, I'm going to have to bend that ruler a lot. And the more I try to bend that ruler, the more it's going to yell at me, try to resist that change. So multinest, that was discussed a little bit in the previous talk as well. We're going to talk a lot more here. Multinest allows us to put an input in a likelihood function, and it's going to return the parameters of best fit, the error associated with them, and the correlation between all those terms. This is different than other tools because it's a Bayesian inference tool.
Oh, sorry.
And it's going to give us the log evidence involved as well. What the log evidence is going to do is, like when I was talking with the ruler of best fit, we're able to check all those different shapes of parameters and be able to see which ones do the job best for us. Different shapes are going to give you different log evidences.
All right, so the toy model. The toy model, essentially, we created, first of all, to get acquainted with multinest, but we're going to use the same approach that we used to it, hopefully to actual neutrino work. So on our model, we simulate some data set that we receive that is a perfect sinusoidal wave. We then apply some background to the wave. We just shift it up and down. That'll be the orange wave right here, and we tilt it a little bit. That'll be the red one. And around that last wave, we spread the points apart. And we simulate that as some data with some background. And we run multinest on it. We have multinest find the parameters of best fit for us. On this plot, all the green lines represents the attempts of multinest as it finds the best parameter, or the parameters of best fit. Yeah. And here is just an example of the return of multinest. It gives us the parameter A, B, C, D, E, and E. This is our model that we use to try to best fit the parameters. The main value of all the parameters and the standard deviation for each of them. And important, it gives the same thing for the log evidence and the standard deviation of the log evidence. And we repeat this process. We assume the model, we give multinest the parameters, we create some data by this random shifting over and over and over and over again, thousands of times. And this is just 100 of the many, many trials that we got, and we accumulate those results. Every time we run it, we save all the output that multinest gave us, and after that we're going to have a big enough number of parameter A, parameter B, parameter C, so on and so forth. We can plot stuff like this. So parameter A, B, C, D, E, and log evidence over there. We get these nice distributions for each of the parameters. We get a mean value for each of the parameters. And we get a standard deviation for each of the parameters, which depends on the systematic errors that we inputted into the background that we made up. And of course, same thing for the log evidence. Interesting to note is the parameter E right here, which is a phase parameter for a model. It does not behave very much like a Gaussian. And it's partly because it is, being a phase parameter, is very sensitive to shifts in any of the other parameters. And that brings back the correlation between all the parameters that we have, how the sensitivity of one depends on the others. And also brings back the idea of a prior. In this case, we assumed a uniform prior for all our parameters. But if you had a good idea of what the parameter E might be, and we applied a prior to it, we might avoid all these non-Gaussian loop things.
So the minor experiment at Texas A&M will be releasing data later this year, and that's a huge deal for what we've been talking about today. The minor experiment is really perfect for what we want to do with it. It allows us to have a movable core so we can change the distances for the mass gap, and it also has very sensitive materials so we can test for those very small recoil energies. Overall, in summary, multinest presents much potential to be used as a method for fitting parameters and comparing models by interpreting numerically calculated functions where the parameter simply scales the axis. We can use multinest to fit those parameters, and by examining the output, we can determine best exposure times and distances from the detector that will produce the most meaningful results. Thank you.
Thank you very much.
Thank you very much for your presentation. So, do we have questions? Yes. How much, the minor experiment, how much range will you have in terms of, so the closest I think you can go is 3 meters. How's the farthest that you can go, before, you can't get enough statistics?
We haven't delved much into the outer boundaries of this. We've been looking at shorter ranges, somewhere between the 3 to 10. If you go back to the original oscillation graphs, we've taken this to be fairly literal because we're looking at 1 eV sterile neutrinos. So we're only going to look for about 10 meters out at most.
Yeah, I mean, the interesting thing would be if